Hello, everybody. Welcome to a special edition of the eVTOL Flight Test Council. Let me give you a short introduction to the council because this is a wide open meeting this time. The eVTOL Flight Test Council is all about best practices for flight testing electric aircraft of all kinds, whether they're conventional takeoff and landing or vertical takeoff and landing or anything else. We care a lot about the electrical stuff. And we have lots of meetings every other week. And we talk about best practices and what are the challenges and certification and various different things. So this is a special session at this special link because this particular event we're going to post on YouTube through Vertical Flight Society. They've been very generous in supporting this council and being right in the middle of doing all this work. And so with that short intro, I would like to go ahead and introduce our guest speaker for today. Now, this is Dr. Steve Foland. He is part of a team that wrote a paper that GAMA has recently published. And I think a lot of you are aware of GAMA, the General Aviation Manufacturers Association. And through GAMA, they published a paper on basically battery performance. So there's the battery side and the energy management side. And this paper is, it's the full title of it is Managing Range and Endurance of Battery Electric Aircraft. And this is actually part of a two-part series that we're going to have this month. Today is Dr. Steve Foland. He's going to talk about the battery side. 2 months from today, almost exactly 2 months, on the 20th of April, we're going to have the follow-on, the part 2 of this. And his co-authors are going to be speaking to us. So more to come on that. But let me just go ahead and introduce Dr. Foland real quick. So he's of course, he's a PhD. He's a principal engineer and the integral battery team person at Beta Aircraft. And his current role is harnessing his expertise in complex systems, simulation, optimization, and algorithm development. His focus these days is high voltage energy storage, specifically performance modeling and fuel gauging, which is so important to every one of us in this meeting. So he's also an enthusiastic educator. He helps at various levels. He's done lots of curriculum training for college level and high school level. And for accomplishing, addressing engineering sciences and different branches and applied sciences and the whole bit. There's hundreds of hours of work on this. And most recently, and to our benefit, he has recently shifted his focus towards aviation education for industry, this audience right here. So we saw a short version of his talk a few months ago presented through GAMA. And one of the leaders of Vertical Flight Society, Mike Hirschberg, and I were talking real time during that talk. And we said, this is the kind of guy who can explain things so well that we wanted him to have a longer audience and a special time to talk about everything in here. So with no further ado, and I think I've stalled long enough to go ahead and get started. Dr. Foland, take it away.
Thank you very much for the warm introduction. I really appreciate it. Let me get a screen share going, and we'll jump right in. So the title of my talk today is Aviation Battery Performance Modeling. As Al mentioned, it is adapted from essentially the first 3 sections of our GAMA white paper, Managing Range and Endurance of Battery Electric Aircraft. And really what this is going to cover is all of the background to the term that we're going to use a lot today is the underlying performance model necessary to bridge the gap between conventional fuel-based aviation and electric aviation. Real quickly here, if I get my slides operating, I want to give a few abbreviations that I might drop in. I try to define things as I go, but just in case I don't, we're going to use the term high voltage energy storage system, which I sometimes abbreviate HVESS. Similarly, ESS is pretty interchangeable in this world, as we'll discuss. State of charge, SOC, and SOH, state of health, are 2 very important terms, as is open circuit voltage, sometimes abbreviated V_OC, sometimes OCV, depending on which author you're reading from. Just real quickly, I collaborated with multiple co-authors on this GAMA white paper. I am from Beta Technologies, as Al mentioned. So, I'm kind of serving a dual role here today. One of them is to present to you something of Beta's energy management philosophy, while also, doing my part to help bring that and the work that we've collaborated on to the industry in the form of, in this case, education on the background and needs of bridging that gap. So real quick, just Beta's battery management philosophy or energy management philosophy is really just to embrace the similarities between high voltage storage systems and conventional fuel whenever we can, but also recognize the differences and develop robust, simple approaches and algorithms to address those. Effective energy management, in short, extends the range of the aircraft, it improves the safety of the aircraft, and it informs mission planning and maintenance cycles. So bottom line is a really solid, robust energy management strategy is going to help bridge that gap between a conventional aircraft and an electric aircraft. I had to work in my co-author, Ryan Nehru from Joby, loved the phrase, "there is no dipstick." It was in many initial drafts of the GAMA white paper before eventually being cut to his chagrin. But on his behalf, I've included here an actual literal dipstick fuel gauge from a 1940 Piper Cub. Really, that is what that is to say, and why that became sort of the unofficial motto of our team when we were drafting this paper, is that there are extremely simple means of measuring fuel level and vis-a-vis performance in a conventional aircraft. There aren't such easy metrics in a battery electric aircraft, but that doesn't mean we can't make it just as safe and effective. So we don't have a dipstick. That's why we're having this talk. Our objectives here today. First, we're going to outline key terminology and concepts in e-aviation energy management. This is a lot of what you're going to see today. If you were on that previous GAMA talk, this is going to be a slightly longer form version of what I skimmed through introducing our full white paper during that presentation. But ultimately, I'm assuming no background, not assuming that people have electrical engineering backgrounds or have seen our prior work. I'm assuming that we have a very broad audience of engineers and other aviation professionals here today. I want to introduce this concept. I told you I'd use this term a lot, the underlying battery performance model, and define usable energy and power capability in particular. We're going to outline effective energy management strategies to ensure safe energy management through all phases of flight, as well as minimize the gaps between those conventional and electric aircraft operation. And then we'll talk about next steps. We'll tease the presentation that's coming in 2 months, talk a little bit more about what our intentions are behind that and how that helps us build a coherent narrative around the management, indication systems, and reserve strategies of battery electric aircraft. So, okay, so very bottom line, there's a lot of similarities and there's a lot of differences between a fuel tank and the HVESS on a battery system. The biggest difference that I can highlight, obviously we've got the fuel tank, which is where your energy is stored, and then we've got the battery where your energy is stored. The biggest difference is that performance capability is really driven largely by getting that fuel to your engine so it can ultimately be converted into fuel output on a conventional aircraft. Whereas, we don't have fuel pumps, we don't have things like that. In a lot of ways, an electric aircraft is a lot simpler than a conventional aircraft because you have such a direct linkage between your energy storage and your power output. However, your power capability, what would be the equivalent of flow rate in your conventional fuel system, is intrinsically linked to the energy state of your battery. You can't decouple them. You just have to account for them. And that's going to be a lot of what we talk about today. How this impacts aircraft level performance is really in this simple way. A conventional fueled aircraft, pictured here on the left, as we go from full to empty tank, we have full performance capability. In fact, if we wanted to get really detailed about it, your performance capability increases because your aircraft is getting lighter as you burn fuel. But for all intents and purposes, we are assuming that your performance capability exceeds the needs of the aircraft until the very last drop, or at least the last accessible drop of fuel, and then your performance capability drops off to nothing. With an electric aircraft, it's different. You're losing performance capability as soon as you start drawing energy from the battery. And eventually, down into deep states of charge, you will lose performance capability at the aircraft level. For a VTOL aircraft, you're going to lose your VTOL capabilities first. Later, you're going to lose your climb capability and so on and so forth, eventually losing full control authority of the aircraft. But that's very deep into states of charge. It's really the more high performance, particularly thrust-borne operations that we're concerned about hitting that performance capability limit when we talk about it. So I will, generally speaking, talk in terms of VTOL aircraft that are also capable of cruise, wing-borne flight, like Beta's aircraft, the AIAA. But most of the principles that we're talking about really apply to any eVTOL aircraft or any electric aircraft powered by batteries. So, a lot of times when we think about progress in energy storage, we think about a graph like this that shows essentially the increases over time in cell energy density. And I could also make an argument that cell power density is very important, usually not pictured on these types of high-level graphs, but it is improving over time. And there's a huge temptation to wait around for energy density to get to the Goldilocks zone that we want before we start, building commercial aircraft. But we can do a lot with the technologies of 2024. A lot of that comes down to building good pack design. So the less mass added as we build out those packs, the better, thermal management, all these things that go into building a pack is going to improve your safety. And if you keep your pack light enough, it improves your range as well. Part of the argument that I'm making today is that your fuel gauging, or essentially your what information you can draw from your battery performance model, and the tolerances that you have on its accuracy are going to be a huge driver for both safety and your range. And that's really important. We don't need to wait around in many cases for the battery industry to battery OEMs to catch up with where we want them to be. We can get the very most out of the technology in whatever present year we're talking about this in through robust, efficient, and well-calibrated algorithms. So, okay, if you will allow me, I'm going to take some slides. This is about 10 or 12 slides that are very much reflecting my background in education. I tend to use a lot of terms around power and energy that are, I think, a lot of times more intuitive in the mechanical world than they are in the electrical world. We can touch things, we can see them move. I personally was raised by a box of Legos. So I've always had a lot more mechanical intuition and have had to work to develop the electrical, intuition and intuition in power and energy and other domains. So I'm going to really break this down. If you're an electrical engineer like me, this is going to seem super simple, but I want to make sure we're all on the same page about specifically what we're talking about. So I like talking about, when we're talking about just very introduction to power and energy and the basic terms in basic electricity, I like thinking of them in terms of an analogy of a pipe, water flowing through a pipe. It's a classic educator's analogy. And we can think of things in terms of both the pressure of that liquid moving through the pipe, and we can think of it as the flow rate, or the rate at which an individual water molecule or droplet of water is actually moving. So low pressure, low flow is obvious. High pressure, low flow, you don't necessarily have to have a lot of water moving for that water that is moving to have a lot of energy, to have a lot of pressure behind it. Of course, you can also have high flow at low pressure that has a different type of energy behind it. And then ultimately, you've got your high pressure, high flow, which is where the real work starts. To get us to this sort of understanding of, kilowatt hours and kilowatts and all the things that go into talking around energy and power, I want to kind of break this down piece by piece and chat about this analogy just a little deeper. So looking at this analogy from water moving through a pipe to charges moving through a circuit, your pressure is basically potential energy. That's in the electrical domain, voltage in volts. It's the ability to push a charge through the circuit. You don't necessarily have a lot of movement of charges at high voltage, but you do have the ability to do it under the right conditions. Once those start moving, essentially an abstraction away from kinetic energy is the flow rate, how much volume of water is moving over time. And it's really important that we just make a distinction between that and the speed at which it's moving. It's the amount. If I were going to measure that through a pipe, I'd probably measure it in liters per second. Over in the electrical domain, we measure it in amps per second, or excuse me, coulombs per second, which is that's the derivation of the unit, the ampere or the amp. So a coulomb is just a measurement of a lot of charge. And so we're moving that charge past a point in the circuit in a given amount of time. It's the rate, not speed, at which those electrons are moving in the circuit. And lastly, we have the resistance, or how hard it is to pass on the water side, the water through the pipe. That might be analogous to the diameter of the pipe or the roughness of the pipe. In the electrical world, it's the resistance of our load. We measure it in ohms. It basically describes the relationship between your voltage and your current. So I've presented this at the university level too, and I always enjoy these. They're a little more fun in person to do these bouncing questions, but we all know, we all did this when we were kids. It's why it's so intuitive. You know, what happens when you put your thumb over the pipe? Basically, if your flow remains constant, but the size is restricted. Of course, that increases the pressure, it goes farther. And that's a very important relationship that, like I said, is very intuitive, but it wasn't as intuitive in the electrical world until this guy came along, George Ohm, I believe it was in the 1830s or late 1820s that he proposed Ohm's law, which describes the relationship between voltage, current, and resistance, usually expressed as V equals IR, or in other words, the voltage is equal to the current times the resistance, or looking at it other ways, it's also often very useful, particularly in batteries, to look at it as current is equal to the voltage divided by resistance. As intuitive as that seems, and as basic as this all is, it actually wasn't well accepted at its time. This is some of Ohm's detractors. In fact, I believe it was the Minister of Education in Germany at the time in early 1830s, who described this as a web of naked fancies and said a professor who preaches such heresies is unworthy to teach science. I've tried many times to come up with a good joke at the end of this slide about him meeting resistance, and it's never panned out. But suffice it to say, sometimes the most, things that seem the most intuitive to us after the fact weren't at the time they were discovered. And I think that's a good lesson to keep in mind as we move through our careers. Okay, going back to the water analogy just for a moment. So we can do work with any of these levels of flow and or pressure. You might do a very small amount of work with low pressure and low flow, and you might do very different types of mechanical work with high pressure, low flow versus low pressure, high flow. Low pressure, high flow, you could move something very big, very slowly. High pressure, low flow, you could probably move something very small, very quickly. But if we want a lot of power, which is the rate at which work is accomplished, we need both. So in the electrical domain, remember, our pressure is effectively analogous to our voltage. Our flow rate is effectively analogous to our current. So power in units, watts, is equal to a volt times an amp. You can rearrange that using Ohm's law and get to I squared R, which is also a very common definition. But the volt amp is a nice way to get yourself back to watts, rate at which work is or can be accomplished. I should say can be accomplished is really referring to power capability. Power is typically expressed in terms of the work currently being done. In the electrical world, we all know low voltage, low current. We need high voltage and high current to get high power in this domain, which is almost always necessary for any of our actual electric propulsion in a battery electric aircraft. Okay, one last analogy, because you know I love them. Another good question and answer here. This is your classic 1,000 pounds of feathers or 1,000 pounds of bricks. In this case, we're talking about a 1,000 kilogram crate and 1,000 kilograms of loose rice, and we have to get them on top of a shelf. Both of these are the same amount of mechanical work. And that's really important to fundamentally understand, is that we use the term work colloquially in a way that is different from the way that we use work in physics. Usually when I present this to university students, they say, depending on one or the other opinion they might have, they think one is more work, meaning it would be a real pain to move it. Same amount of mechanical work. You're still moving a mass over a distance against a force. Just the tools you would use is different. So you'd probably use something very powerful to move your crate, whereas you might be able to use something very small. If you had enough time on your hands, you could use a pair of tweezers and move them one at a time. The important distinction here is one takes lots of power, one takes lots of time, but they both get us to the same amount ultimately of energy. Energy in watt hours is the total amount of work that has been done or can be done. So when we think of that in terms of a battery, it's the total amount of charges we could move through a circuit throughout that battery's discharge effectively. Okay, now that we have that behind us, I will pause just in case there's any questions that we want to highlight, but I'm sure this is relatively basic stuff. I just wanted to make sure we're all level set and on the same page. All right, that silence means it's time to move on to our next section, which is the underlying battery performance model. So battery models can be very, very complex. They can be very, very simple. There's a lot of diversity. They can range all the way from molecular level solutions to reaction kinetics, and they can go all the way down to very simple empirical models. That's really the other axis of this that isn't pictured here. We're looking at complex to simple or micro to macro. But there's also a level of discrepancy in terms of how much the model physically describes about what's happening in the battery. Your complex models are typically physical based, usually some derivation of the Doyle-Fuller-Newman model for lithium-ion batteries. But more generally, they're just solving the Butler-Volmer equation that describes the relationship between reaction rate and the electrical potential or voltage between the electrodes and the electrolyte. Those can be very complex, and there's ways to reduce that complexity. Even if we're talking about a physical model, you can reduce the complexity of your geometry and assume that all your particles are of uniform size, or in a very popular model, treat everything in sort of one dimension with your other dimension being a pseudo dimension. It's called the pseudo two-dimensional model. Those are great ways to reduce it. You can use model order reduction, or you can reduce it all the way down to the point where your model no longer represents anything physically about what's happening in your battery. It just describes kinematically how your battery is going to perform in a circuit. Most of the time, those take the form of an equivalent circuit model, which we're going to be talking about today because it's a useful analogy. And a useful way to look at things to kind of intuit ourselves into the mindset of how a battery is going to intuitively respond. Everything has trades here. More complex models are beneficial in the sense that they give you more in-depth knowledge of the battery. Simpler models are advantageous because they're usually quick and easy to calculate, and it means that we can usually run them in real time. So it depends on what our goals are. We're going to talk in terms of an equivalent circuit model for now. Your most basic equivalent circuit model literally just models your battery's open circuit voltage as a voltage source that varies with both state of charge and time, and a series resistance, here R0, usually called the equivalent series resistance, that is effectively treated as inside the battery. Your terminal voltage is the voltage that appears at the outside of that, and then your load current is going to be what actually gets to do useful work. So you've got your cell here, that's where your cell boundaries are. This is where your electrochemical energy is, and this is the loss model for this battery. Everything out here is your usable energy, the things that actually get to the thing we're trying to do work with. In our case, an electric propulsion system. So R0 is your equivalent series resistance. That term is important because it's going to impact how this works. Now note the direction that I drew I load here, the load current. I draw it that way specifically to make batteries that are charging have a positive current and batteries that are discharging have a negative current. It's useful for a lot of calculations and intuition, this being one of them. Let's consider a battery that's discharging at a constant current. Its terminal voltage is going to be decreasing, and that is going to be primarily driven by the fact that its open circuit voltage is decreasing as charge is removed or as state of charge is decreasing. If we change that load current by some delta I here, delta I1, we're going to get a corresponding change in voltage, delta V1, which is equal to that just Ohm's law, I over the change in R, or excuse me, just the change in I over R. And that also goes the other direction. So if we have a positive delta I2, we get an increase in our voltage. And these are very simple things to visualize and measure. I usually shy away from showing actual battery data when I'm not behind an NDA, but I have some battery data to show you today. This was borrowed from a 6th grade science fair project that Al kindly sent to my inbox from his son. This is just a terminal voltage measurement of a battery powering a fan. And you can see here the decrease in the terminal voltage, and you can also see some really nice jumps in your battery's voltage as it's disconnected and then subsequently reconnected to the fan. It's pretty cool stuff. It's a great science fair project, and I hope he watches this YouTube video once it's uploaded eventually. All right, so there are limitations to something this simple. First and foremost is the fact that your battery's voltage does not respond instantly. If you think about the kinetic energy that's happening inside the cell, ions need to move across your electrolyte, and reactions need to occur at the surface of your electrodes, and those take time. So typically what you'll see here is not a sharp edge to your voltage change. If you're measuring it with fast enough equipment, you'll see a exponential change. And then you'll see that on the other side as well as it recovers. Basically, shouldn't have said exponential. It's a natural logarithm shaped curve that decays from the original point to where it's going to end up after it changes. And we just don't get that from a simple equivalent series resistance model. But we can if we add a little bit more complexity. So this is a very typical Randall's equivalent circuit model, second order, meaning we have 2 resistor capacitor pairs. It's the same idea. We still have our cell boundaries. We still have our electrochemical energy represented by the variable voltage source. We still have a loss model. Our loss model is just now more complex and allows us to essentially roughly model the dynamics that we see at varying states of charge in terms of the time constants that those things like ionic diffusion and reaction rate actually take to ramp up and ramp down. It's still not a kinetic model. These resistors and capacitors don't really exist. In fact, typically this would be, if you wanted to do it a perfect kinematic model, this would be an infinite series, a Fourier series of resistors and capacitors. Obviously complex from complexity standpoint, that's hugely disadvantageous. So we typically truncate it to 2 or 3 orders of resistors and capacitors, which captures enough of those cell dynamics in what we see at the output for our usable energy for our purposes, or at least for some purposes. So we actually do from this circuit see what we're expecting to see, or very close to it. And the quality of that underlying performance model is going to directly impact the accuracy of fuel gauging, mission planning, and everything else surrounding that. So, okay, so let's talk potential versus usable energy. So if we consider the integral from 100% state of charge to 0% state of charge, and state of charge is expressed here as a percent, but if we want to sanity check ourselves, state of charge could be converted into amp hours. So we have amps times time on our x-axis. We have a open circuit voltage or potential on our y-axis. Voltage times current is watts. Watts times time gets us to watt hours. So we can integrate that and end up with a very nice total electrical chemical energy number for that system. That's usually your nameplate capacity on a cell, and then that becomes your nameplate capacity multiplied by however many cells you have in series and parallel into the full battery pack. When you're actually discharging this, you're not going to see that open circuit voltage. You're going to see, just like in the simple experimental data I showed, you're going to see some energy lost. You won't see your battery's open circuit voltage at the terminals. You'll see whatever you get after it gets to the terminals through that battery's loss or loss model, here represented by the red region. Power demand is up, representing what is effectively a simple CTOL takeoff profile on the upper graph there. And all the energy that's below that is your usable energy. So that's how we define the term usable energy. Anytime I'm talking about that, I'm not talking about all the energy in the cell. I'm talking about what we can actually get to. Now, taking that a step further, if we put a VTOL profile over this, now we're going to have more loss. More current drawn from the battery means more voltage lost, means less potential at the terminals, means less usable energy. Additionally, there may come some point, and there almost definitely will come some point, where the amount of power you're demanding, if you in fact have a large amount of power, like something like a VTOL landing, you're going to come to a point where that's going to hit some minimum voltage. It might not be the cell's minimum operating voltage. It might actually be the minimum operating voltage of your electric propulsion system or your inverters or anything else. That eventually makes the energy below that point inaccessible simply because how you want to use that electrical storage system is not compatible with its actual power capability. So power capability is a driver of usable energy, and our energy state or our current state of charge is a driver of power capability. Like I said at the very beginning, they are intrinsically linked. If we look at that from a practical sense, looking at both VTOL and CTOL profiles here, we're going to have to leave some reserve energy on the table, shown here in light gray. But as we look forward from our present point in the flight, the VTOL mission profile is seeing less usable energy, or it should be seeing less usable energy. The OEM of that aircraft must account for less usable energy than for the CTOL profile, where we have less loss, and we may even potentially be able to dig deeper into that energy state as we approach the bottom of charge. There are other dynamics here that I have left out or will just skim over because they add a lot of complexity to these diagrams, and they're for a high-level talk like this, they're not worth kind of getting ourselves in a twist over, but they're worth mentioning. State of health or the aging of the battery is going to both decrease capacity and increase loss inside the cell. You lose capacity as side reactions and evaporation and other things take electrolytes out of your, take ions out of your electrolyte. And as some of those ions are lost, they end up in side reactions at the surface of your electrodes that end up forming a passivation layer on your electrodes that make them less effective at having chemical reactions occur because there's less surface area. That increases the decrease in ions, decreases your capacity. The formation of a passivation layer increases your loss. Both are important, both impact usable energy. Conversely, temperature actually improves performance of your batteries. So at a high temperature, most of your electrical system in the aircraft is going to start performing at worse performance. Your batteries, because they are ultimately driven by electrochemical dynamics, improve in performance. You get a little boost in initial capacity as those ions become a little bit more energetic, and you get less loss as those ions become quicker to react at the surface of your electrodes. Thinking of this intuitively, we all know that a flashlight gets dimmer and dies faster as cycle life increases. That's an analogy we put in there. I like to use the analogy of my cell phone, because we've all had a cell phone that eventually starts dying particularly quickly as its battery gets older, and we eventually have to replace it. The flashlight gets brighter and lasts longer with increased temperature. I don't know if you've ever taken, back in the day, we used to store batteries in the freezer sometimes to make them last longer. And when you took them right out, the flashlight wouldn't be nearly as bright until they warmed up. From the perspective of conventional fuel, you have the same energy regardless of temperature or fueling cycles. Your tank doesn't shrink over time. It doesn't, the extra energy in your fuel when it's hotter or colder doesn't have a significant impact on performance of the aircraft. So this is a very serious thing that we need to consider. And it's very important that we track these, even though I said I wasn't going to spend a lot of time on them. They are important for an OEM to track. Going back to my old cell phone that I mentioned, something that you may have had experience in is when your cell phone gets old, sometimes it'll drop from like 15 or 20% battery to zero in an instant. And that's because there's not a lot of pressure on cell phone OEMs to have particularly accurate aging models for their batteries. And your battery is performing off model. It thought it had more percentage left, and then it suddenly realized it didn't as that loss started tanking your terminal voltage, and all of a sudden it just drops off. We obviously can't have that in an aircraft scenario, which is why this is so important to discuss in detail. So, okay, in summary, I won't belabor it, but for batteries, they are going to deliver less energy as we discharge more rapidly or as we draw more power from them, and they are going to fade over time. From a power perspective, they have a discharge limit, and that power capability degrades over time. And the power requirements and basically the structure of your electric propulsion system may drive and size the battery not around energy, but around power. Obviously, most of those things are not true with conventional fuels. Again, why modeling here is so important. And I'll pause for any questions. All right, we'll save them for the end and keep rolling. Oh, did I hear somebody unmute?
Yeah, Steve, this is Pete Karras, FRL AFWorks. Hey, quick question for you, because we're starting to see a lot of electric aircraft come through our wheelhouse, including you guys. Is there a way to monitor battery degradation before a pre-flight so that you kind of know as you charge and discharge, just like you would with like your computers, every time there's a cycle time where you charge or discharge it, that cycle time builds up and it kind of degrades the battery over time, which means you might see it as 100%. Hey, I can go fly, it's 100%. But then as you start flying, it starts degrading faster than predicted. Is there stuff in place to predict that so that when you do pre-flight planning, you know what the battery life actually is before you go fly?
I'm glad you asked that question. I actually added a slide a little later in the presentation that addresses basically that.
Oh,
My short and diplomatic answer is going to be that will be OEM specific until the civil aviation authorities come to a firm decision on how this will be handled. But there are many different ways it could be accomplished. The important thing is that it is accomplished, and I will get there. I'm also aware of some prototype and experimental aircraft that we've worked with as well that do exactly what you're describing. So this is a known issue, and this is exactly what we're trying to avoid with the underlying performance model.
Gotcha. And do you think there's going to be systems on board that will be able to do that for you?
I think some of it will be on board, some of it will be off board.
Okay, so the pilot operating handbook will probably cover some of it based on flight hours or cycle times. We're probably going to have to monitor cycle times so that we know accurately where the batteries are at each of them. Probably have to maybe barcode them so that we can manage them through some kind of a maintenance or an R&M schedule, I'm guessing.
What you're basically describing is usually referred to as a semi-empirical aging model. So
Okay.
a semi-empirical aging model basically says, hey, okay, so I cycled it this many times at this temperature to this depth of discharge. I discharged it this long. Then it sat in the warehouse or the hangar for this long. Then I flew it this many times. How much do I expect it to have degraded in terms of energy and power capability? And that would get you in the ballpark. And then some of it will have to be truly empirical with some form of either onboard the aircraft or off-board diagnostic system that again, one of the goals of writing this white paper was not to dictate specifically how OEMs solve this problem, just to point out the problems that do need to be solved.
Okay. And are you familiar with any aircraft or systems that do that right now?
Well, we're certainly in the process of developing those systems ourselves, and I'm sure many others are.
Okay. All right. Thank you.
Thank you. All right, so next we're going to outline some effective energy management strategies, and specifically we're going to highlight some of those pitfalls that we were just discussing, which was a great segue here. So let's consider a circumstance here. This is very different than having a cell phone at 15% in your pocket. We are here at relatively low state of charge. We are flying. We can see here from the power demand that we took off in a VTOL configuration, most likely. And we're now wondering what happens next. What performance do I have left in my aircraft? So here's one of those onboard modeling systems that, this is a cartoon, a simplified diagram, but this is the kind of thing that an OEM would implement. So first and foremost, we have input, which is our power demand. And we're going to have some process noise on that. Obviously, not all of your input and not all of your power demand makes it directly to the batteries, and there's all kinds of delays and other things that affect that. But after that process, it reaches your plant model or your battery. That battery is going to have some quantities you can output and measure, but all of those measurements are going to have some noise. So we represent that there as some added noise in the system. And ultimately, at the end, you get your measurements, which typically include things you can directly measure like voltage, current, and temperature. Those are imprecise, and they also lack insight into what's actually happening with the energy state of the battery. This is what happens to the cell phone at 15%. It has one voltage that it sees at the terminals, and then suddenly your power demand increases, maybe you open a new app or increase your brightness, and the terminal voltage drops and it realizes it was lower than it thought it was. This is what we need to fix. Fortunately, if we have a good battery model, we can also pass that input into that model and predict how it's going to perform. Furthermore, from that, we can compare what we expect to measure from the battery model to what we're actually measuring. And we can, through a statistical model, typically some form of Kalman filtering or other statistics-based filter model, we can correct our measurements, we can update our battery model, and we can output an estimated energy state. So that's going to approximate your energy state plus your battery model gives you power capability, etc. Again, these could be as simple or complex as we want them to be. But this is where your model lives. Your model lives in this prediction. The concept of running, for all intents and purposes, I'm going to call it a digital twin alongside your actual battery asset to compare their performance. Okay, so let's go back to our example here. So if we consider two upcoming power profiles, one for vertical landing, one for conventional landing, we're going to have two different expected responses of our battery model. And what we might find is that a conventional landing goes just fine and even can go farther because it's effectively sipping from the gas tank. It's not demanding a lot of power, so we get more energy. But we might find that our vertical landing craters our voltage or has enough essentially loss to give us not enough usable energy available for that. Even though that might be a shorter mission, it might even be using less total energy. It's just that the usable energy has changed. And that's very important to understand, and it's even more important to model. Ultimately, what we're basically talking about is this. So if you look at this from a different perspective, we could model state of charge and the power demand curve and consider what our maximum power demand that we can accomplish or our power capability is at all states of charge. Again, this is a very simplified diagram. The shape ends up a little bit different, but it's surprisingly not too dissimilar from this, the basic shape for an actual lithium-ion battery. We would get from that a battery beginning of life capability envelope. We might also, if we had uncertainty in our model, derate that capability envelope to account for those uncertainties in either measurements or the model or anything else. From there, we could consider some mission profiles. We have variable cruise energy, so basically we're taking off vertically here, we're cruising for some amount of time, and then we are going through a landing, which increases our power demand. You might have some conservative VTOL mission profile, and then your model could help you understand what a max range VTOL profile is, which is basically when your power demand curve meets up and intersects with that derated capability envelope. Here, BOL is beginning of life. But we also have to consider that our battery is aging. This is where those semi-empirical and empirical aging models come into play. We also have to consider that what was a conservative mission profile at beginning of life may become an aggressive or even an impossible mission profile as those batteries age. Again, not dictating how OEMs fix that, but they do need to address it. This also means that your actual state of health is not a scalar quantity. And I've seen that pitfall, to Pete's question earlier, I've seen that pitfall many times in very simplified readout systems, just like the one on your cell phone, just like the one on most consumer electronics, that give you a percent SOC, and then they may even give you a percent state of health. Oh, I'm at 85% state of health. And I look at that as a battery engineer, and I say, what does that mean? Is that 85% capacity? Is it 85% power capability? It's really a vector. It's many things. It's not a scalar quantity, and that's very important to understand. There may be some cases in which you display it in a simplified manner, but in the underlying battery performance model, it still needs to maintain that complexity so that we can understand how performance will behave. When we think about where this is the slide I was referencing earlier that I added recently. This is where the battery model lives, could be a few different places. Typically, we think of it in terms of airborne software. It's going to take place on some kind of battery management system on the aircraft. And certainly for fuel gauging purposes, some of this battery model needs to live there. There's also the pilot's operating handbook. There's also ground or cloud-based planning tools if OEMs want to go down that route, all of which could contain some or all of the battery model and could handle some or all of the algorithms to update that battery model. There is no rule, at least currently, that states that these need to use the same complexity performance model. It's entirely possible that you could use a simplified model that is conservatively derated in the pilot operating handbook and a much more complex model to understand cell kinetics on the ground on a server somewhere in the cloud. So there's, again, many different ways an OEM could address this. I'm not here to tell them how to do their jobs, but it's worth noting that there's a myriad of ways we could solve this as long as we solve it. So, okay, so let's talk some complexity and performance trades. These are just spitball examples to show ways in which a OEM might choose to take the conservative route and trade for basically performance or range of their aircraft, and how they could also increase or improve the performance of their model and get that range or performance back. So let's say they can only demonstrate plus or minus X% accuracy of their performance model. And that's going to be true of all performance models, but let's say that X% is big, like 10%. Well, there's nothing saying they can't use that model. However, they would need to derate their battery by that percent. If they can only demonstrate that it's accurate to within plus or minus 10%, great, your beginning of life capacity and your capacity throughout all phases of life is now derated by that uncertainty, as assuming you can demonstrate that that uncertainty is something that your unknown is known, essentially. Or they could spend the time and trade the complexity to develop a more accurate model, which I hope most would, because as I stated before, we're trying right now to get the most performance we can get out of the battery technologies of today, which is limited, and we want to get every last dropout. So what if, for example, cell capacity or power capability is not uniform as packs age? These packs, like I said, they're high voltage, high current. There are many packs, many cells in series, and those cells are in parallel cell groups. They're not going to age uniformly. Either the OEM could bound their entire pack's performance by the weakest cell group, or they could track performance in each cell group independently and aggregate it appropriately. Obviously, one of those is much simpler than the other approach. Obviously, the more complex approach gets you more usable energy out of your model and thus expands your performance envelope of the aircraft. Similarly, what if cell imbalance is impacting their performance model? Your cells are never going to be charged to the exact same state of charge. Well, you could either put boundaries on accepted imbalance and then derate accordingly, or once again, your performance model could take imbalance into account. All of these things, I've mentioned a lot of modeling at the cell level, the complexity of how much of the reaction kinetics versus how much of the cell external dynamics and kinematics we're actually tracking. There's also a lot of complexity in how you build that up into a full pack model. Do you model the whole pack as one battery? Do you model it as many batteries? How deep into that do you go? The answer is as deep as you want to go, and your performance will improve if you do it. So, all right. Let me dig into our next steps here, tease the next one, and then we'll break for questions. I'm not too much over time, I don't think, here. Ultimately, we want to build a cohesive performance management, indication system, and reserve strategy for battery electric aircraft. That is the bottom line. Whether those are lift plus cruise VTOL aircraft like ours, whether they are tilt rotor aircraft, multi-copter, it could be anything. They could be conventional aircraft. We need some cohesive framework that accounts for all of these challenges that they all face. The concept behind fuel management, this is really a Part 135 thing, and the language really hasn't been updated in a while. The language of the concept of a reserve fuel amount dates back to about 1946 from an advisory circular. I think it got updated the last time in 1978, and then the language has more or less stayed the same in every iteration. That basically states very simple time-based reserves, here demonstrated graphically. Essentially, you have some mission maximum range, and then you have to be able to maintain flight for X minutes afterward. That becomes your reserve energy, X being 30 minutes for most cases, depending on your type of aircraft, of course. So what does that 20 or 30 minutes reserve do? Well, it tells you how much fuel you need to carry, but it doesn't tell you what that fuel or what that energy needs to be able to get your aircraft to do. In the case of a more complex energy storage system like a battery, like we've discussed here, carrying 30 minutes of cruise capability just tells me I can fly around for 30 minutes before I find where I'm going to crash the aircraft. It doesn't tell me whether the aircraft is going to be capable of performing that landing, whatever style of landing we're doing, at the end of that reserve period. Which means that if we're talking about something like a reserve VTOL landing, we're going to have to actually carry more energy, because I sure hope our OEMs are accounting for the fact that they're not going to be able to access all that energy. It's not all usable because of what the performance model tells them. That doesn't really take these kinds of complex performance models into account. Ultimately, what we proposed in the white paper was taking all the safety intentions that a 30 or 20-minute reserve is intended to accomplish. Everything from go-arounds, instrumentation uncertainty, adverse weather conditions, etc., and split it out into all the things we really know. Have an awareness of performance capability, be more adaptive to more complex missions, be more inclusive of off-nominal factors, and be integrated into the display to the flight crew in the ways that we can in a more modern era of aviation. What that gets us to eventually, I'll let my co-authors take it away in 2 months from now, gets us to a proposed model of something that could tell you where all your alternate routes are, what your capabilities are, how much capability margin you have at all points through your flight, and really help you understand what your aircraft is capable of. This is not fully compatible with current time-based reserves, but a performance-based reserve strategy, if we were eventually to adopt it, would be able to accomplish all of the same safety intents, I would argue better than existing frameworks, while also unlocking more potential performance out of future aircraft. All right, we made it. I'll open the floor for questions, and I'm happy to chat. I see some hands up. I will go ahead, Al, if you want to moderate the questions. I'm still trying to wrap my head around switching from presenter view here.
All right. I'll probably best do that there we go, Scott.
All right.
Yeah, a great presentation. I mean, it gets a lot into the complexities that you don't really think about unless you're a battery engineer. But it seems like the last slide, it seemed to tell me it's like in terms of like certification rules and those types of things, this complexity either comes out by accounting for it in mission planning and more of the operational environment, or in a certification environment. And I'm just kind of wondering, say, maybe since Beta is involved in certification at the moment, how does that get? How do you write the cert basis and the rules and everything else? Because this is almost like pulling up to a gas station, and you never know how much energy is really in the gas that you're putting in a tank. I mean, it just seems like there's a whole level of complexity beyond kind of the normal fuel-based planning.
There certainly is, and I think the theme of most of my answers, I'm going to share my screen real quickly again, because I think this particular slide is quite relevant. Hopefully you're all seeing that. The point that we're really making in the white paper is not that we want to make the path harder for OEMs, and we got. I encourage everybody. Hopefully, in the YouTube description there'll be a link to this white paper. I encourage everybody to read it, because, like I said, this really only covered about the first half of the paper. Part 2 will hopefully dig more deeply into the actual strategies around it. But the argument that I would make here is that we're not trying to restrict OEMs to a difficult pathway. We're trying to unblock them to more performance-aware pathways that might give them the capability of extending their range, given the fact that the complexity that you're describing is already going to have to live somewhere. This model either has to live in your aircraft's airborne software. It has to live in a very D-rated capacity in your pilot operating handbook. It has to be somewhere. And there's going to be trades for it, whether that trade is complexity or performance envelope. And the idea behind this slightly more complex proposals that I teased there is that an OEM that was doing the full extent of their due diligence of modeling and performance and flight planning and all of these things could extract all this information that we couldn't have back in 1968, 1978, when the language I was talking about in Part 135 was solidified. And that would get them a lot of advantages. But they could also stick to the old framework that would still have all the same intents. They would just have to trade that for the performance hit that it would take. It looks like Andre has a hand up.
Hey, can you hear me?
Yes, I
Yeah,
can.
Andre, go ahead.
All right. So very good presentation, Steve. Thank you. My question would be, is there a standardized way to build a model that you showed on the screen just now, like a TSO thing that any battery manufacturer could run through this test suite and come up with a model, or that's something that is still up down the road?
No, we wouldn't be investing as much money as we have in battery test infrastructure if we trusted all of the data that we get from battery OEMs. Unfortunately, we are still a very small player from the scale of other industries that consume lithium-ion cells, to the extent that, number one, battery OEMs are not willing to invest an enormous amount of time and energy into meeting our specific needs. And additionally, they don't understand our specific needs. This could be standardized down the road if the framework were put in place for it. There are many well-established models in literature that could be used for this. I don't necessarily think that dictating a specific style of model, like I said, I think leaving the power in the hands of OEMs to define how and where they want to make their trades is the way to go. But there could certainly be standard performance tests, for example, that would allow you to extract all the information you'd need for these models. And I'd love to get cooperation from battery OEMs on that as well. But that's another area of legwork that needs to happen that's a little outside the scope of what we talked about today.
Okay, thank you.
Okay, we've got another couple of minutes. We can give you guys a chance. I'm going to post something up here. I'm going to share my own screen in just a moment.
Yeah, I just
So
want to say
Steve-
while we're waiting for questions to come in, and I'm sorry to whoever I cut off, I just wanted to thank everybody for their time today while I still have everybody on the line. And I wanted to thank Al and VFS for giving us this opportunity to share this collaborative work that we did.
Absolutely. We're so delighted that you have taken the time for us.
We've got a hand up.
Okay, C. Smith.
Oh, there we go. They're speaking of collaborators.
It's been a great presentation. You had a really interesting slide earlier that I believe was showing different cathode technologies and potential watt-hour per kilograms in future states. What do you think with next-gen battery technology? How do you think the battery model and the complexities of battery models really differ from more commonplace NMC type batteries today?
Yeah, that's a great question. So the extent of something like the Doyle-Fuller-Newman model is really primarily to conventional lithium-ion batteries. There are effects that we're seeing with some next-gen batteries, lithium metal batteries and things like that, that you don't see in conventional lithium-ion batteries. Again, these are parts of the performance model. In particular, they're parts of the performance model that would be hard to capture in a conventional equivalent circuit model. So there may be pressures either to develop better lumped element models in the future or to adapt things like pseudo 2D models built around Butler-Volmer to capture more of those cell dynamics that, like you said, we don't see them throughout the typical performance capability envelope of an NMC or an NCA cell, but we do see them in others. Really, just to take this a step further, I think the importance of all the discussion that we had here today is that that concept, even though I just said that equivalent circuit models don't capture everything, that concept of understanding the trades between your energy stored under your voltage curve and your usable energy that's driven by demand through your loss model is a really important one to understand, because it applies to all electric aircraft, not just battery electric aircraft. If we're talking hydrogen, if we're talking hybrid, all of these are going to have to do the same things, just maybe in slightly different ways. Maybe their governing equations are going to be different in their model, but it's still going to have to follow all the way back to the basic electronic slides I went through, the basic understanding of trading for voltage and current when we're trying to get usable energy at a given power demand. So I think, generally speaking, I think it's going to have to be accounted for. I'm sure it'll be accounted for in many different ways. That's part of the intention of all this, is to draw attention to the fact that this is an area that needs some interest, whether it's from battery OEMs, us, civil aviation authorities. It's good to have these conversations.
Great, thanks for answering that.
Okay, looks like we have one last hand raised
Okay.
on the dial-in.
Steve, now, this is John McKeown. I can't get my hand up there. Just a quick question or comment that the acid test of what we're doing is really going to be in pre-flight readiness, if you would. So, given all the uncertainties in, you know, whether it's battery manufacture, battery life, environmental conditions, when somebody completes his or her mission planning, we have to have a reliable way of estimating, you know, battery life, you know, at the outset of the mission with the appropriate reserve. And obviously, we don't want to be toting around useless energy, but so it will be a challenge for us to collect the data and then, as you're saying, model it. But that's what's gonna, I think, what's gonna make or break it for us in terms of affordability, if you would, for practical applications, you know, much further down the line. But what a great presentation! Thanks a million.
Thank you so much. I really appreciate that, and I couldn't agree more. It is this kind of thing is going to make or break us. We talk a lot about our discussions with civil aviation authorities, but I think just as much emphasis needs to be placed on operators and ground maintenance crews, because you're completely correct. There's a lot of bits and pieces that are going to go into operating these aircraft that, like I said at the very beginning of this presentation, there's lots of parts of an electric aircraft, simplifications in the drivetrain, for example, that have much less maintenance down the road than a conventional fueled aircraft. But there's also things that we've never had to account for before. And I think your point was well said, that it's going to make or break success in all these discussions.
Okay, we have one last dial-in caller with a hand up. Go ahead.
Hello, I'm Owen McMahon. I work at a vertical lift research and development company called Unmanned Aerospace, and you know, thank you for the presentation. It was very, very interesting. So what we've realized at our company is that because of the increased energy draw at different stages, you know, VTOL stages of the flight, that a hybrid energy generation scheme could actually be quite advantageous. And during the high energy draw moments, you tap into a booster battery, and during lower energy draws, you can try to charge that booster battery. I just wanted to know if you guys, you know, had done any kind of modeling or looking at, you know, regimes like that.
I'm sure the Beta legal team would be after me if I said specifically whether we have considered that. You bring up an excellent point. I will also say that something that is currently not on the horizons for most OEMs that I'm aware of, but is another variation on hybrid that you're talking about, is right now most of the cells that are being developed, high performance cells, travel sort of directly up an axis on increased energy capability and increased power capability. There's also potential operating regimes where someone might have a high power performance pack and a high energy performance pack paired in a sort of pseudo hybrid arrangement, just like you described, because yes, you do have these wild swings in performance where sometimes you're drawing so little energy that you just want as much of that energy as you can get. And other times you want access to that energy as fast as you can get it, but it's a relatively small amount of energy. It's honestly why I burned 10 minutes of my presentation on the basic power versus energy discussion to make sure we're on the same page. There's a lot of different configurations, and I hope the industry explores all of them.
Okay. So let me go ahead and do a few wrap-up comments. Again, Steve, this was great, and one of the things that we want to talk about, and let me summarize again the council. This is the eVTOL Flight Test Council. We do best practices for flight testing. That's our niche, but of course, a lot of this is the design work and so forth. I'm Al Lawless. I'm the chairman of the council. And we try to do something like this every couple of weeks. We have a meeting talking about one thing or the next. A common thread throughout Steve's talk and almost everything we do is collaboration. A lot of what we've heard today is there's a lot of proprietary information out there. And that's all good and fine, but the problem is the regulators don't know how to approve stuff if everything is a secret. What the regulators are looking for is industry consensus. Now, that doesn't mean you need to tell a manufacturer needs to say their secret sauce. But if the manufacturers can get together and talk about how to get this stuff approved, if there's industry consensus, then the regulators can flow along with that. And so that's my pitch to everybody, is to say, keep this in mind as you're going through this. How can we collaborate on this? And of course, and that's exactly what GAMA is promoting. That's exactly what Steve is promoting and so forth. So please keep that in mind. I have the contact information. We're going to have this posted on YouTube very soon. And in 2 months, on April 20th, we will do part 2 of the GAMA paper. And that will be about the energy management side. And I think the best way to think of that, my favorite euphemism for that is getting energy out of a battery is like getting money out of a bank. You go to a banker for a loan. The first thing they ask you is, how much money do you have in my bank? Because the more you have, the more they're willing to give you. It's that with batteries. And as a little teaser, we'll have part 2 in 2 months. So thank you, everybody, for attending today. We had a record turnout, and we'll be back in 2 months for the next one. Take care.